Greetings once again, AP Calc students. Mr. Record here from Avon High School. And what you doing? Yeah, what you doing? We're going to take a look at a problem from a fairly recent Continental Math League exam from Meet 3. That's the 21-22 season. A problem number 6 that involves finding the volume of a solid of revolution. And this problem, it's very important that we review this a little bit with my students, especially in the AB course, because we haven't quite got to this particular topic. It's coming up in the next unit. We typically hit this a little bit after spring break. It's topic 8 point, it's kind of like 8.10, 8.11, straddles those two particular parts of the course and exam description. But I think I can give you guys a pretty good depiction about what's going on. So let's take a look at this problem. It says the region in the first quadrant bounded by y equal a times x, y equal 1 over a times x, where a is positive, and the line x equal 1 is rotated about the x-axis. We are to find the volume in terms of a. Now, we don't have this very specific a value, which is a little bit of a disappointment, I suppose, right? And that's, I think, what makes these problems a lot more difficult and challenging on the Continental Math League than they say they would be in a traditional calculus course or on the AP exam. So what I want to do is I want to just spend a moment getting an idea about what this graph would look like. That would be these two functions sketched on a single coordinate plane. And notice that I only bothered to graph the first quadrant here because that's really all that matters. So let's just maybe pretend for a moment that maybe a is a number that's pretty close to 1. Close to 1. For all intents and purposes, we could think of it as 1, even though it says it's got to be bigger. Because I just want to get this kind of an idea that this is a graph of a line that goes through the origin, and it has a slope that would be, well, it's not 1. I said it's got to be bigger than 1, right? So we'll say that it's maybe just like 1.2 or something like that. I just don't want to draw something that's too crazy steep. Now, the next thing that we have to do for this particular problem is sketch the 1 over a times x. And for that particular graph, what we're going to have to do is we're going to think about what 1 over x looks like. Okay, now 1 over x is a very traditional graph that every student should know what that sketches, right? A good calculus teacher might even give a summer packet where that graph shows up. Well, maybe we did that, I don't know. So what we'll do here is we'll sketch this in a different color. And if we can pretend that a is about equal to 1, what we've got is something that looks like this. And there is another branch over here, mind you, but that branch does not matter to us because we're only dealing with quadrant 1. Okay? Now, what's going to happen next is we're going to graph the line x equal 1, because that is another part of our sort of what makes up this enclosed region. And the problem is that it's kind of difficult to tell, where is 1 in relation to maybe this x value here that would serve as the intersection of those two graphs. Well, we could find that point, and I don't think that that's something that's too terribly difficult if we just set the ax equal to the 1 over ax, right? And then in just a short minute, we can cross multiply. We can solve for x squared, and then we can take the square root of both sides. And so we actually get 1 divided by a, right? Now, if a is larger than 1, what side of 1 over a would 1 lie on? I'm going to let you think about that for a second. What side of 1 over a would the value 1 be on? And if you said the right side, good for you, because you are correct. And therefore, I'm going to graph the green vertical line, x equal 1 there. I don't have to graph all of it because if I stop right there, I have an enclosed region, and that's what we're looking for. All right, those of you that are, at this point in the game, if you're my students, you know a little bit about area between curves to an extent. That's kind of what we're thinking about here. We want this enclosed region so that we can work on this, but we're not going to find area. We're going to find the volume. And the volume is going to be created when we revolve this or rotate this about the x-axis. So picture this, if you will. Picture this yellow region rolling around the x-axis, and it's going to create a three-dimensional shape. Unfortunately, it is a three-dimensional shape that I cannot even begin to draw. Now, I could try. You want to have a good laugh here. I could try to draw this, and it would look something like maybe that. And then if I kind of three-dimensionalize it, oh, I've just ruined the picture, haven't I? Pretty much have ruined the picture. But you kind of start to get to see that it's a very unusual three-dimensional shape that's got a little hollowness in it. That's what I wanted you to see, because there's two different ways that we can find a volume of a solid of revolution. One is called the disk method, which is a little easier. And the formula for that, as we're going to talk about very much in detail soon, is pi times the integral of some radius value, and I'm going to say of x, because that's what we have in this case squared, and then we have a couple of boundaries on our integral. Unfortunately, this is not a disk method. This is not just a simple cylinder, and think about it. A cylinder is exactly what you get if you take a rectangle and you revolve it around an axis. Spin that rectangle all the way around, then you have a very thin cylinder, right? Like a coin. And isn't the volume of a cylinder pi r squared h? And the h is this delta x or dx. Yeah, that's how it works. But unfortunately, that's not what's going on in this problem. This problem is a little harder. Yeah, we get the hardest kind of problem before we start to learn it. What you're going to use is what's called the washer method here. Washer meaning there is a hole in the middle. And the washer method is just volume equal pi. Sounds familiar, right? But now you integrate the capital R squared, but you're going to subtract a little r squared with respect to x. And again, there's going to be some boundaries and all those kinds of things going on. Well, now the big question is, how do you get the capital R? Well, to get the capital R, you just simply figure out how far it is from the axis of rotation all the way up to your graph. That blue rectangle is my capital R. The length of that blue rectangle is just simply what you get when you take the equation or expression for the top of it, which is the a times x, and subtract the equation that you get for the bottom. And I say the word equation, I really mean the expression after the y, right? This is the line y equals 0, of course, the x-axis, and we just subtract it from the a times x. Okay, now what about this little r? Well, little r is going to be this red rectangle. It's going to be any rectangle, right, between your shaded regions that emanates from the axis of revolution but stops at the nearest edge of your shaded region. And the little r of x is going to be defined as the expression that constitutes the top, 1 over ax, minus the expression that is on the bottom, which is 0. And so now you have a fighting chance. You've really come a long way in this problem once you find capital R and little r. I always remember capital R is the big one, little r is the small one when you compare them. So if we square ax, we get a squared x squared, no argument there, right? And if we square 1 over ax, we get 1 over a squared x squared, all with respect to x, right? And then our boundaries of integration are going to go from the left bound of 1 over a to the upper bound of 1. Now, there are several calculators on the market that are suitable for use on the AP Calc exam that will handle this expression. I think you just have to make sure that you put a multiplication symbol in between any kind of random constant like a, b, c, etc., and your variable x. But I want to show you that this is very, very easy, to integrate by hand. If we drop the constant a squared down, integrate our x squared, which is x cubed over 3. And then we do the same thing here, drop our constant 1 over a squared down. Now careful, integrate x to the -2. You get negative x to the -1, which I believe is going to look like that. And it's right about here where I am going to, good sound effects, we're going to put on the brakes, and I'm going to have you guys plug in 1 for the x, carefully plug in 1 over a for the x, and subtract those. You don't have to simplify much. Maybe give yourself a shot at trying to simplify it a little bit, but I don't want you to be too disappointed because it doesn't simplify a whole heck of a lot. And that's not really what the focus of this problem is going to be, the simplifying. It's really all of the setup and introducing you to this idea. Okay? Now, before I sign off here, I want to tell you that if in the event on any kind of problems that you see, whether you're practicing for the CML or whatnot, let's say you saw something like this. Let's say you had just one curve and it was bounded here by the x-axis, and this was your shaded region, right? And you're going to take that shaded region and you're going to revolve it. I want you to know that whenever that happens, there is no washer. You only have a disk method, because when you draw that one representative rectangle from the axis of rotation, it never goes through any white space like we're seeing up here. And so that would use the disk method formula, where this is capital R, and of course this one we already said is the washer. So I know that that is just a super quick crash course over this, and I wanted to make sure that this video was only about 12 or 13 minutes to introduce this idea, but that should get you kind of rolling with this new idea so that you can practice this problem on that particular CML. So anyway, best of luck, and we'll see you next time.